Hi, everybody, and welcome to a video on introduction to power cycles. So let's get started. Okay, this is a little schematic that I'm going to use. You're going to see it lots of times in this video. It's a schematic of a system operating in a cycle. And here's the roadmap of what we have. It may take a while. First is Dr. Barbish put out set 3 of his homeworks. And when I read problem 4, this problem is superb for a number of reasons. It was well thought out, it's well worded, and given your progress in this course, as you work through it, and I want to encourage those in Dr. Barbish's class to work through it. If you're watching the video, encourage you to work on it if you have time, because it can prepare you to perform well on the upcoming test, because just about everything that's there is work that you've already done. And I hope that most of it you have in your head, the skills that you've developed. And so it's a very involved problem. Without a lot of experience, it might take you a few hours to work on and complete this problem, but you're going to find it will be well worth it. Now, so standing on its own, it's a superb homework problem, and I'm going to try to go through the steps of explaining how would an inexperienced person begin to work on the problem and solve the problem. Then I want to add some remarks about, give you a little crash course in general of systems operating in a cycle, which this homework problem illustrates. And then also, how do we quantify the thermal efficiency of a system operating in a cycle? Very important, very powerful. And if you haven't covered that in your class yet, I want to give some more remarks about thermal efficiency of a cycle. So here we go to work on Dr. Barbish's set 3, problem 4. And we want to thank him for coming up with this problem. Here's the screenshot, and here's what folks have received. Consider a piston and cylinder assembly that contains 1 pound mass of water. So I have drawn in a piston and cylinder and trying to show a little bit of a sketch here, H2O, 1 pound. It undergoes a power cycle. Got it, shown in the TV diagram below. And he says the pressures are, the highest pressure in the process is 1,000 PSI. And the lowest pressure is 100 PSI. So let's look at what your homework is. You're asked to find the heat transfer Qn for each of the 4 processes. Let's satisfy ourselves that we got a cycle. We've got 4 processes: 1 to 2, 2 to 3, 3 to 4, and then 4 to 1 takes us right back to where we started. That's a cycle. Okay, so your part A. Determine the heat transfer Qn for each of those 4 processes. Okay, that's kind of a lot. Okay. Also, find the work out for each of those 4 processes. That's even more work. Part B, determine the change in internal energy for the cycle. That's delta E. Okay. Part C simply says, add up all the Qns add up all the Qs that you calculated and give me an answer. Part D, do the same thing for the work values, add all 4 of them up, see what you get. And then part E says determine the thermal efficiency. And you can't do that until you've had the classroom material. And then I'll try to give you the crash course here on what is thermal efficiency. Talk about that more later. Okay, so a little bigger screenshot of what you're trying to do. Now, part B is basically a trick question. Because if we went back and looked at that cycle, you see that we start and end at the same place. A little bit more of that later, but essentially it's delta E for the cycle is E1 minus E1, which is 0. Okay. Part B, this is where you're going to add up all the Qs that you found for part A. Part D, add up all the Ws that you found for part A, and then E, the thermal efficiency. And this is going to require some classroom work, or at least looking at my crash course for the definition of thermal efficiency. So a lot more than just a formula. All right, so note, here's the way this is going to be the outline of how I solve the problem. How would I solve the problem? The first thing I do is I go to a pressure volume diagram. I'm going to draw this out on pencil and paper on my own. And the reason I go with the PV diagram is because it gives me a chance to visualize the work out for each of the four processes. Remember, for a closed system, piston and cylinder here, work out is integral of PDV. Integral PDV is the area under the curve on a PV diagram. That really helps me out. Okay. And the other thing, of course, I see is I'm sort of repeating that I'm starting out as a saturated liquid at 1. That's given in the problem sketch. Saturated vapor in state 2 given in the problem sketch. Okay, and observe that it's a cycle. The beginning state and then the ending state are one in the same. The next thing I do before crunching numbers is I set up a table. I plan ahead, a table that I need to populate. So I've got 4 processes. I put those in row. Here, my first column is labeling the processes. So I've got 1, 2, 3, 4 rows. Then I've got 3 columns because first column is W out. I'm supposed to calculate the works for each of those. I'm going to populate 4 things here. I've got a column for Q in for each of the 4 processes. And then I've got delta U because looking ahead towards part B. What's the change in energy for this? For the piston and cylinder, there's no change in kinetic energy, no change in potential energy. So all we have to worry about in terms of energy change is internal energy. The next thing I did was think to myself, how will I proceed to populate the table? First thing I'm going to do is work on the work because I can see it with my eyes on the PV diagram. The next thing I'm going to do is jump over to delta U because I see that with my PV diagram, I can get U values for all 4 of those states. So I'll work on delta U next, and I'll save Q in for last because as I think ahead and plan my work, I remember when you're asked for Q, this can pay off for you in a quiz or a test. When I'm asked for Q, it's very predictable that you're going to use the first law of thermodynamics for a closed system, for this case, to solve for Q. It's like a little hint. So I save that for last. Okay. And then the sums. So notice here, parts B, C, and D, you're summing up the columns to get parts B, C, and D. All right. So let's go back to our PV diagram and note we're not crunching numbers yet. Let's just note down whether work values are going to be positive, negative, or 0. Let's look at process 1 to 2. Area under the curve. I see it. It's our rectangle, the area under the curve, and it's an easy integral. It's pressure, it's constant, times delta V, V2 minus V1. So here we go. So notice the note I wrote down. If I were doing this with pencil and paper, I'd scratch that down on my paper. Work is positive. It's a positive number integrating left to right. And it's going to be the mass times the pressure times little V2 minus little V1. And I'll bet I can get that from the steam tables. Process 2 to 3. What's the area under the curve? 2 to 3. See it with my eyes. It's 0. Numerically 0. Got it. Process 3 to 4. Constant pressure process. I can see the area under the curve is a rectangle again. And the value is going to be a negative number because I'm integrating from right to left. Again, quiz prep, test prep. Okay. So there we go. I'm just going to write it down, pencil and paper. The work out from 3 to 4 is M integral PDV or M P4 or P3, doesn't matter, times V4 minus V3. All right, might be a little tricky getting V4 and V3, but we're going to get it. And then the last process, 4 to 1, I see with my eyes. Area under the curve is 0. I'm going to write it down, 0. Okay. Oh, boy, am I glad I put this green note to myself so I could say it. notice that each of you has got to figure out a way to label your variables, because this is a complex problem. You have 4 processes, so you can't just write down W. Can't do it, right? So here's what I did. I always write down, for me as a student and a practicing engineer, I always have W out, always write W sub out. But then I've got W out 1 to 2, W out 2 to 3, W out 3 to 4, W out 4 to 1, the little subscript. So even inventing your own subscript process, that's up to you. Do whatever you want, but just writing W out, that's not a recipe for good partial credit or a problem that might be like this on a quiz or test. This is a complex problem. I can't imagine that all of this problem would be on a test. That's a little too time consuming, but parts of it could be. All right, so let's update your table with work entries. Do you see that you can immediately write down with pencil and paper zeros, 2 to 3, the work from 2 to 3 is 0, 4 to 1, 0. Write that down. That's some partial credit, okay? But I need V2 and I need V1, I need V3, I need V4. So I got to go back to my PV diagram. All right, so let's make some notes now. Again, you haven't started with your calculator work. You've still got numbers to get. All right. Well, let's look at state 1. How I'm going to need V and F. I'm sorry. I'm going to need V and U for state 1. How will I do that? I see it's saturated liquid. I've got the pressure. I'm going to go to the pressure table, and V1 is going to be equal to VF at 1,000 psi. U1 is going to be U sub F at 1,000 psi. Got it. I'll write those numbers down. State 2, it's saturated vapor. It's on the, it hits the vapor dome. Okay. So V2 is V sub G. U2 is U sub G. I'll write those down. Now, I need V3. How am I going to get V3? I observe from my PV diagram that I've got a vertical line, 2 to 3. That means V3 equals V2. Specific volume 3 equals specific volume 2. Well, what do I know? Okay, can I get the quality? Can I get the quality? Can I get X3? I think I can, because look, V3 equals V2, so I've got a number. Then I can go and I can look up V sub G and V sub F at 100 pounds per PSI, 100 PSI from my pressure table. Now, my text box has obliterated where G is. Sorry about that, but at least you can kind of see where F is. It's over here at the vapor dome. So I can solve for X3 is V3 minus VF. It's a proportion divided by VG minus VF. So it's this length divided by, I've obliterated it, but this length all the way over to the edge of the vapor dome. You get the idea. So it's a proportion. Numerically, I'll solve for that. This is where I will start putting pencil to paper and calculator to get X3. Back to state 4. How do I get X4? It's damn close to the dome, but it's not on the dome. It's a little shy of it because V4 equals V1. It's a vertical line. Exact same approach. Ditto, the same approach for X4 as you did in 3. So now you've already written down V sub G and V sub F. You've got those written down. So all you got to do is the calculator work to determine X4. It's going to be a little number. Look how close it is to the dome. X is going to be a little number for 4. Okay, so then let's see, remaining work before we move on to tabulating our results. States 3 and 4, we need to get little u. I've got to move my zoom, bar here. Okay, states 3 and 4. Once you have X3 and X4, go back and find U3 and U4 using your understanding of the definition of quality. U is equal to X UG plus whatever's left over, 1 minus X times U sub F. That's easy for me to remember. You may have a little different approach for remembering how to get U. Okay. There's a formula in the book that's nearly identical to this, but it's different. It's algebraically different, but it's the exact same mathematical statement. That's up to you. Okay. So this is the way I remember how to get it, because it's like proportions. It's the proportion of vapor times U sub G plus the proportion of liquid, what's left over, 100% minus X, U of the liquid. That's the way I remember it. I keep in my head. I don't look at a formula sheet. Okay. So here we are, step 2. Now it's plug and chug to get these 4 numbers for the 4 processes. You've determined all of those on your own from the steam tables, and the mass, I think, was 1 pound mass. All right. Now we'll move ahead. Now we're trying to populate this Q column, QN. We're going to write down the first law for each of the processes. Okay. And so remember that W out was nothing for 2 to 3 and 4 to 1, so I X those out. And so now back to the calculator. You've got numbers for all of these things. You've got numbers for the work. So plug and chug for all the QNs. Some will be positive, some will be negative. Okay. Determine the thermal efficiency. We're going to jump over this because numerically it's pretty straightforward now that you have populated your table, but this requires the crash course on cycles to define what is thermal efficiency of the cycle. So we're going to jump over this. Back to recap on the PV diagram. It's a very powerful thing. Now you've solved the problem. If you're in Dr. Barbish's class, you've spent a couple of hours on that. Let's see some other valuable things to see from the pressure volume diagram. And that is that you've got what was asked for, W cycle. What I call it traditionally is W net, the net work produced by the cycles. Remember, we had a big number here, rectangle, and a negative number here, a smaller rectangle. And if you do some thinking, you can determine that the area bounded by this cycle is the net work. So W net is the shaded area enclosed in the cycle. Another thing to observe, look at the direction of the process. It is clockwise. So this is a system operating in a cycle producing positive W net. Clockwise, going clockwise, positive W net. That's something you need to learn. We're going to go the opposite direction at a later time in class. Okay. And so what this means, I'm trying to write this out in words, and this is a way to say the cyclic integral of work. The integral sign with the circle, that's a cyclic integral of incremental work. The cyclic integral of all the works is W net. Now, for those of you, I hope that some of you might be thinking about going to graduate school. And so this nomenclature is classic of what we do in graduate school, rather than just saying W net or W cycle. It's the cyclic integral of work. So for those of you thinking about graduate school, maybe a little introduction to that. Okay. But for everybody, going to graduate school or not, recognize that you can visualize the net work for any cycle by looking with your eyes. The area inside the cycle is the net work on a PV diagram. Very cool. Okay, and so this is your congratulations. So for those of you in Dr. Barbish's class, or those who wish to take on a little extra, congratulations for spending the time and effort to numerically evaluate all of the stuff I just talked about. So it's going to pay off for you. Now for our crash courses, 2 crash courses. Oh, before the crash courses, I'm going to blaze through this appendix, keeping English units straight for energy-related situations like this one. Okay. For those of you crunching the numbers, working with pressure and work. So recognize that work has units. Work in English units is going to have units of foot-pounds force, okay? And so ultimately, you're going to be wanting to get your pressure in terms of pounds per square foot. So when I'm working on these problems, immediately transform pressure in PSI, pressure in pounds per square inch, PSI, into pounds per square foot, okay? And so work is going to have the units foot-pounds force. Now, also in the problem statement, it said express all of your answers in terms of BTUs. That's a British thermal unit. BTUs. That's a measure of energy similar to, not equivalent to, but similar to joules in SI. So remember that foot-pounds force is also a unit of energy, and so there is a conversion between BTUs, British thermal units, and foot-pounds force, and I fished that out for you in your conversion tables. Okay, and so this is just a real quick reminder. Oh, and also when you go to your STEAM tables in English, remember what the numbers that you're writing down are BTUs per pound mass, BTUs per pound mass for internal energy and enthalpy when you need it. And then finally, just a reminder, you need to be intimately familiar with this first law of thermodynamics for a closed system. Do not depend on a formula sheet if you're allowed to have a formula sheet. You must commit this to memory for success in this class. Q in minus W out is equal to delta E, which is equal to delta U plus delta KE plus delta PE. Commit that to memory. And of course, I'm saying this because everything in the equation must have the same units. Units must be consistent throughout from left-hand side to right-hand side. Units must be consistent. That's Common Sense 101. All right, so now for the crash course, systems operating in a cycle. I do want to stress that you need to read your text in addition to just looking at this video and or just sitting in your classroom. That's not going to win the day. So this is a crash course version of section 2.6 in your textbook. Now, getting good at this important part of thermal systems analysis, it can launch your career and it can sustain your career. Some people are going to be interested in this. I encourage you to continue to work, continue the hard work of getting good at this. Some could care less. Okay, I can live with that. Most mechanical engineers are going to have to do something with energy and power, no matter what interests you. So at least you have to kind of have a working knowledge of this stuff, even if it doesn't turn you on. It's okay. I respect that if you're not really charged up about this stuff. Okay, so now back to work here. Sketches. You heard me always start with a sketch. Well, in getting ready for quizzes and tests, here's a piston and cylinder. That's a sketch, isn't it? It's a sketch of the equipment. Here's a sketch of a PV diagram of our homework problem here. And the point I want to make is these things, those are sketches, and they feed into, they sort of represent, or they're the guts of what goes into this box. This is a schematic diagram of a system operating in a cycle. And so this box, now, remember I kind of made that point about a PV diagram going clockwise? I'm depicting my little box with a clockwise block arrow. There's a reason for that. My professor, when I was you, my professor insisted that we draw this little arrow inside the box to depict that we're making power, we're going clockwise. Man, that really paid off for me. That's all I can do is pass along to you. That really paid off for me. Okay, and so this is the schematic. So we're going to dissect this schematic. So recognize that this stuff goes into this box. So the box represents the system operating in a cycle. Next slide. Okay, so let's observe what's inside this box and what isn't. Okay, so first thing is I see some arrows, but There's no mass crossing the box boundary. That's what makes it a closed system. So the box is a closed system. No mass is passing in or out of that box. Only forms of energy are crossing the box boundary. And those three big arrows represent forms of energy. QH is traditional heat added. It's like QN. It's heat added into the box. QH, Q high. QL is heat that is leaving the box, heat that's rejected from the box. Okay. And I'm going to talk a little bit more about that, but please do recognize that this is a little different than what I've been preaching about. QN, QN, QN. This would kind of be QN equals a negative number. Heat is rejected from the box. This arrow, W net, is being produced inside the box and it's leaving the box. It's being delivered by way of a shaft or electric power going out to somebody who's using it. Okay. The next thing let me go back a slide. I missed the box is a system operating in a cycle. And for jargon, and at the graduate level, we call this a heat engine. This is called a heat engine. System operating a cycle that's producing net work or net power is called a heat engine. Okay, now next thing to look at on our schematic of our heat engine or our system operating in a cycle. Look at these gray things called with label TH and TL. These are heat reservoirs. We consider these unlimited sources of heat transfer or unlimited sink of heat transfer. TH is held at a high temperature TH, and this reservoir must be hotter than or equal to the hottest temperature within this box. Okay, I'm just going to say that and leave it there. It's a constant temperature reservoir at a temperature TH. TL is also a heat sink reservoir. It's at a constant temperature TL, low temperature, and it has to be colder than or equal to the coldest temperature within this cycle system operating in a cycle. And so why am I saying this? Well, on its own, heat only flows from hot to cold. So that might have been the first or second day of class you covered that. On its own, heat only goes from hot to cold. Okay, now we're going to address part B of that homework problem, the change in energy for one cycle. So remember, I need to remind you, energy E, that would be kind of like U plus KE plus PE. It's a property of a system. Well, if it's a property and our starting state exactly ends our ending state, it's a property. The property is fully defined by the state. So the change in energy E for one cycle, I got to move my Zoom box here. The change in energy E for a cycle, delta E is E1 minus E1. That's exactly 0. And so, so the answer to part B of the homework is delta E of the cycle is 0. That's kind of cool. Now, the next really cool thing is we're gonna use that. Delta E is 0, and we're going to apply the first law of thermodynamics for a closed system for a cycle. Now, I've taken some screenshots from your book, section 2.6.1, energy cycle balance, and I have clipped out equation 240 that says W cycle equals Q cycle. That's a correct statement. However, my opinion is that you need to get familiar with a little more traditional statement of the first law of thermodynamics for a cycle. So if I were teaching you, if I were your instructor in class, I'd say that textbook is correct, but we're going to add some stuff in class that I feel like is a more thorough statement of the first law for a cycle. Okay. Since delta E is 0, so remember, first law for a closed system, Q in minus W out equals delta E. We just showed delta E is 0 for a cycle. Q in minus W out equals 0. Therefore, the cyclic integral of heat in equals the cyclic integral of work out. That is where we start at the graduate level. That's what we start at. But this is valuable for graduates and undergraduates alike. The cyclic integral of heat in equals the cyclic integral of work out. Now, let's see how that compares. How does that relate to our schematic diagram? Can we visually see the cyclic integral of heat in? Well, it's QH going in and QL going out. That's the cyclic integral. That's studying everything from a big picture, not looking at every single process, but from the schematic, the high level. I've got heat flowing in, heat flowing out. So the cyclic integral in terms of numbers, if this is 10 units and this is 3 units, I've got 10 minus 3. 10 minus 3. Okay, that's the cyclic integral of heat in plus 10 minus 3. Okay, cyclic integral of work out. Wow. So here on my schematic, I only see one arrow that's related to work. So I just plop down the cyclic integral of work out. It's just W net work. So here's my little eye icon. And it's looking at, so I'm suggesting that the value of the schematic is looking at it so that you can write down the first law for you can write down the first law of thermodynamics for system operating a cycle without going to your formula sheet. These arrows have to balance. The arrows must balance. And so I've got 1 in and 2 outs. They've got to balance. The cyclic integral of heat in equals cyclic integral of work out. QH minus QL equals W net. Or you could rewrite it. QH equals W net plus QL. Beauty of the schematic. Use the schematic for systems operating in a cycle and use your eye. Okay, next crash course. Thermal efficiency of a system operating in a cycle. Let's now, we're getting somewhere. We're getting near the end. So if you're falling asleep, try to hang in there. Thermal efficiency, very important. Okay. Thermal efficiency has got the, I need to go down there. I didn't put subscript there, so I'm going to need to correct that. Let's go down and look at this. This is eta thermal. Eta, this is not N. This is not the letter N. This is the Greek letter eta. So please do me a favor. Remember this. Don't write this out on your formula sheet. This is not N thermal. This is eta thermal, Greek letter eta. Okay. So when you get out in the working world and you call it N thermal, that makes you look like you're not very well educated. Okay. So you want to represent yourself and your university very well. So you're going to learn that this is Greek letter eta. Thermal efficiency. Oh, now, how do we remember this? How do we remember it? What's the definition of thermal efficiency without going to a formula sheet? Here's the way I remember. This is the way I was taught it. The thermal efficiency for a system operating in a cycle is defined by the energy sought divided by the energy that costs. So can you remember words? It's easier to remember words than it is to remember formulas. Okay. But so let's see, what does this mean? The energy sought. What are we seeking to do if we're running a power plant? If we're running an engine, what are we seeking to do? We're seeking to do work. We're seeking electric energy, or we're seeking to lift a weight, or we're seeking to have a rotating shaft with a torque at a speed. That's what we're seeking to do, W net. Energy that costs. Well, that's what we have to purchase. We have to purchase energy to keep this high temperature reservoir at a constant temperature, or we run out of gas, we run out of heat. So we've got to buy something to keep this high temperature heat source going. So that's what costs us is QH. The thermal efficiency of a heat engine, system operating in a cycle, is energy sought over energy that costs. Please try to remember that. Okay. So why is QH energy that costs? And so here's my answer is you have to imagine that you own or operate a power plant, or you own or operate a car engine. Those are all systems operating in a cycle. Systems operating in a cycle. Well, you've got to purchase that energy in terms of fuel, got to purchase that energy that's needed to make the power. So the energy that you purchase is not the power, is it? It's something that's used for combustion, okay, to maintain the temperature of a high temperature heat source. Okay, so I hope I've given you enough words so that you can remember thermal efficiency of a heat engine, of a system operating in a cycle, energy sought over the energy it costs. And that professor of mine and all of the Virginia Tech mechanical engineering instructors ascribed to this word definition. And boy, it really paid off for a huge amount of people. All right. Why is thermal efficiency important? Why is eta thermal important? Well, the reason is that thermal efficiency quantifies, you get a number for this, quantifies the proportion of energy in terms of heat that you purchase that can possibly be transformed into work. So thermal efficiency quantifies something. It quantifies how well you're transforming heat into work. Okay, now another step, this is going to help you in your thermodynamics homework solving problem. It's going to help you in terms of your quizzes and test performance, applying the first law of thermo to a system operating in a cycle. So here we remember QH minus QL equals W net. So that's the cyclic integral of heat equals the cyclic integral of work. That's the first law of thermo for a cycle. Now, definition of thermal efficiency. Energy sought over the energy cost. W net over QH. Wow. I'm kind of looking at the slide. I say, I can replace W net with QH minus QL. Okay. And now I've got something. Okay. And do you see that I didn't write it on my slide for a reason. Okay. Of course, this would go, if you're allowed a formula sheet, this would go on your formula sheet. And I can only highly recommend that you write these words out on your formula sheet too. Now, you could also write out another equals 1 minus the quantity QL over QH. 1 minus the quantity QL over QH. You could add that to your formula sheet. But in my world, I think you don't need a formula sheet. All right, so thermal efficiency, and how does this relate to the world? Okay, thermal efficiency, eta thermal, is a key way to compare methods for producing electric power. So I got 3 screenshots. There are others, but I've got a nuclear power plant. This is the Surrey power plant in Virginia. I've got a coal-fired power plant. This is the John Amos power plant right outside of Charleston, West Virginia. This is a cutaway view of a General Electric gas turbine generator, a gas turbine generator. It's not a jet engine. This sits on the ground and it produces electric power. The fuel for this General Electric gas turbine generator engine is natural gas. So all of these have 3 different types of fuel, but all of them have the same functionality, is making electric power. And so all of these, they all operate at a steady rate, so many BTUs per hour. BTUs per hour, that would be a rate. Kilowatts, that would be a rate. That's kilojoules per second. All of those operate at a rate continuously. And the thing is, all of these 3 power plants and more can be reduced to this schematic. And so this is why we engineers in practice are able to compare. How are these 3, how do they stack up against each other in terms of efficiency? And we can answer that. So when you get through this course, you're going to be able to answer that question. So, but they can all be reduced to this basic schematic. Okay, so let's recap the power of a heat engine. A heat engine, it's a system operating a cycle. It is a method that can be operated 24/7, 365. It can be operated continuously to transform energy in the form of heat into energy in the form of work. Or in other words, from a thermal efficiency standpoint, you're transforming the energy that costs into the energy you're seeking. The thermal efficiency is energy sought divided by energy that costs. So I hope that helps your understanding of where you're going in class. Let's review what we covered. We looked at really an awful lot of details that would enable you to solve Dr. Barbish's Set 3 Problem 4, that excellent homework problem. If you take the time to do it, you will prepare yourself for your quiz and certainly will prepare yourself for the test. You won't have this question, it's way too complex, but I can almost guarantee that some aspect of this problem is going to be covered on one of your tests, no matter what section you're in. Okay. We covered a crash course on systems operating in a cycle. And then we took it one step further to quantify how well is that system operating in a cycle working. We defined thermal efficiency. So we covered a lot of territory here. I'm going to have to check to see how much time I covered. It might be maybe a little too much. Maybe you can watch the video in little chunks, but that's what I've got. So I thank you for watching the video, even if you had to watch it piece by piece by piece. Don't hesitate to go back and look at this video when you can get confused about systems operating in a cycle. And also want to encourage all of you to look at Dr. Barbish's homework problem, allow a few hours to work on it, and it will pay off for you in the long run. So good luck with it.